Welcome to our session on debugging techniques. Debugging is the essential process of identifying, analyzing, and removing errors from your computer programs. It's not just about fixing a broken line. It's a systematic approach to ensuring your code behaves exactly as you intended. Today, we'll turn you into a professional code detective. Think of debugging like solving a detective mystery. Your code is the crime scene, and the error is the mystery you need to solve. Instead of guessing, you gather clues like error messages or strange output to trace the evidence back to the source. A good programmer doesn't panic, they investigate the evidence logically until the mystery is resolved. There are three main culprits in our mystery. First, syntax errors occur when your code violates Python's grammar rules, like a missing parenthesis. Runtime errors happen while the program is actually running, such as dividing by 0. Finally, the trickiest ones are logic errors. The program finishes without crashing, but the result is mathematically incorrect. The oldest and most reliable trick in the book is using print statements. By placing print functions in key areas, you can peek behind the curtain to see exactly what values your variables hold at any given moment. It's like installing security cameras in your code to see exactly where the data goes wrong. Here is how you implement this. We've defined a price and a discount, but we want to confirm the calculation is correct. By adding a prefix like debug inside our print function, we can clearly see the output in the console. This simple step confirms the value of final_price before the rest of your program uses that data. While print statements are helpful, they can become messy. That's where the versus Code Debugger shines. It's a built-in powerhouse that allows you to pause your code, inspect variables, and follow the execution line by line without cluttering your logic. It's the professional standard for identifying exactly where your program drifts off course. To use the debugger, look at the margin to the left of your line numbers in versus code. Click that space to place a small red dot. This is your breakpoint. When you run your script in debug mode, the computer will freeze at that specific line, letting you examine the state of your application exactly at that moment. Once your code is paused, you gain control over the timeline using the debugger toolbar. Step over moves to the next line in your current file. Step into is critical because it takes you inside a function, allowing you to see exactly how your logic processes data, while step out quickly jumps back to the parent code block. The watch window is your best friend. You can manually add variable names here, and as you step through your code, versus code will update their values in real time. This is incredibly powerful for spotting the exact loop iteration or conditional check where a number or string value changes into something you didn't expect. The call stack section tells you the story of how your code arrived at its current location. If you are deep inside a complex function, the stack lists every parent function that was called to get there. It's like a trail of breadcrumbs, helping you understand the sequence of events leading to a specific bug or crash. Even with perfect logic, your program might encounter unexpected issues, like a file being missing or a user entering text instead of a number. This is where exception handling comes in. By wrapping potentially risky code in a try block, we can catch the error in an except block, allowing our program to log the issue and continue running instead of crashing. Here is a classic example. We attempt to divide 10 by 0, which is mathematically impossible and would normally stop our script. By placing this inside a try block and catching the zero division error, we print a friendly message instead of a scary red traceback. It turns a fatal system error into a manageable event for the user. Loops are a common source of headaches. If your exit condition is never met, you end up with an infinite loop that freezes your terminal. To debug this, set a breakpoint inside your loop. By stepping through each iteration, you can watch your variables change and see exactly why the loop isn't terminating as you expected. Logic errors are the trickiest bugs because the computer doesn't see anything wrong, it just does exactly what you told it to do, even if that's not what you wanted. If your calculation is off by 1, verify your steps manually. Print out intermediate values at each stage to ensure your data matches your expectations before the final output. This is a famous industry technique. Explain your code line by line to an inanimate object like a rubber duck. By forcing yourself to articulate exactly what each line is supposed to do, you'll often hear the mistake in your own explanation. It sounds silly, but it is one of the most effective ways to find logic errors in your code. It's easy to litter your code with temporary print statements while hunting for bugs. My biggest piece of advice is to clean these up before you commit your work. Leaving print debuggers in your finished project makes it messy and slow. Instead, look into Python's built-in logging module, which allows you to toggle messages on or off without cluttering your logic. When your code crashes, Python displays a traceback, a wall of text that looks intimidating. Don't panic. Simply scroll to the very bottom line. That's where you'll find the error type and the exact line number where the issue occurred. Treat this not as a failure, but as a roadmap provided by Python to guide you straight to the fix. In this example, calling divide with 0 triggers a zero division error. The traceback will explicitly tell you the error name and the line number where the division happens. When you see this, you know your logic failed to account for a zero denominator. Always check the file name and line number printed at the bottom of the stack trace. When your lists or dictionaries grow large, standard print statements become impossible to read. Use the print module, which stands for pretty print, to display your data structures with proper indentation and sorted keys. This makes spotting an incorrect value in a massive nested dictionary much faster than staring at a single, unformatted line of text. Assert statements are a fantastic way to validate your assumptions during development. By writing assert followed by a condition, Python will crash the program immediately if that condition is false, effectively flagging a bug the moment it happens. It's a great way to catch bad data entering your functions before it causes errors deeper down in your code. Time for a quick knowledge check. Which of these tools is specifically designed to give you a live, detailed view of your variables while your code is paused at a breakpoint? Is it A, B, or C? If you picked B, you are absolutely right. The watch window is your best friend for real-time inspection. To close out, keep your programs robust by using try-except blocks to catch unexpected errors gracefully. Use assert statements to verify your internal assumptions while you develop. Above all, maintain your patience. Every bug you encounter is simply an opportunity to learn something new about how Python works under the hood. Happy coding and happy debugging!